So we continue with the uniform convergence. So now we talk about uniform convergence of sequence of function. So now uniform convergence of series. So we say that summation from n equal 1 to infinity of f sub n of x, so this is the definition, converges uniformly, so by definition, if and only if the sequence of partial sums as n of x equals summation from n equal 1 to n of fn of x. So this is now a sequence of function. Yes, now big Sn is a sequence of partial sum Sn converges uniform. Okay. So this is the same as if you remember from Math 1, what is summation from an from n equal 1 to infinity? It's by definition the limit as n goes to big N of summation from n equal 1 to n of a sub n, and we say that this converge by definition because this sum doesn't make sense, but we say this converge if this limit exists. So now we say that a series converge uniformly if the sequence of partial sums converge uniformly. But as you know from Math 1 also, that it's easier to prove that something converges than to prove to where it converges. It's hard to find the limit of a series. It's hard to find the value of the series, yes? For example, you used to, in Math 1 to know the summation of 1 over n factorial times 2 power n converges, but when you never calculated what the limit is. But to know that this converges, for example, you use in Math 1 ratio test. Okay. So now you need like some kind of test to check that a series converges uniformly. So this is the Weierstrass M-test. It says the following: if absolute value of fn of x is smaller than mn for all x in I, and so mn is a sequence independent of x, and summation from n equal 1 to infinity of m sum n converges, this is now a sequence, there's no x here. If this series converges, then summation from n equal 1 to infinity of fn of x converges uniformly. Okay? So if I can bound my function by a sequence such that the summation of this sequence converges, then my summation of my function converges uniformly. Well, this goes only like if you have fn smaller than mn and then summation of mn diverges, this doesn't mean anything. Yes, this goes only one way. If the summation of mn converges, then summation of fn converges uniformly. If summation of mn diverges, then it might converge uniformly and it might not converge uniformly. So an example. We know that the Fourier series of absolute value of x. So what was the Fourier series of absolute value of x? Sorry about that. So the Fourier series of absolute value of x was equal to, I should find it now, okay, to pi over 2 minus 4 over pi summation from k from n equals 0 to infinity of cosine 2n plus 1 x over 2n plus 1 squared. Okay, and we know since I mean the periodic extension of absolute value of x is PC1 and continuous, that the Fourier series of absolute value of x converges pointwise to absolute value of x. We know this, that this is in fact equal to f of x. And now the question is the convergence uniform? Okay. So what is I'm asking here? So I'm asking, this is Sn of absolute value of x, and this is equal pi over 2 minus 4 over pi, the limit as n goes to plus infinity of summation from n equals 0 to n of cosine 2n plus 1 x over 2n plus 1 squared. And now the question is if this series converge uniformly. Now you know that, let's try Weierstrass M test. This is the only test you know to prove uniform convergence of series. So I know that absolute value of cosine 2n plus 1 x over 2n plus 1 square, this is smaller than 1 over 2n plus 1 square. So I can bound it by 1 over 2n plus 1 square. And the summation of 1 over 2n plus 1 square converges. Why? Why? Because if you want, 1 over 2n plus 1 square is very close to 1 over n squared. And then you have 1 over 2n plus 1 square over 1 over n square. This is equal n squared over 2n plus 1 squared, which goes to 1 over 4. And then by LCT, it converges. Okay? And all you can do it by comparison test. You have 1 over 2n plus 1 square, or is smaller than 1 over n square. And summation 1 over n square converges. And that's it. So by DCT, summation of 1 over 2n plus 1 square converges. All this is fine, okay? I mean, for me, it's enough to write this, okay? This course here. So this is comparable to 1 over n squared. So they converge. This is like using LCT, okay? This is some parameter. So this is like p test, p equal to 2. Summation of 1 over n squared converges because this is p test, p equal to 2. P series. Okay? Therefore, by Weierstrass M test, summation of cosine 2n plus 1 x over 2n plus 1 square converges uniformly. And this implies from n equal 1 to infinity. And this implies as a Fourier series of absolute value of x, which by definition is the limit as n goes to infinity of pi over 2 minus 4 over pi, summation from n equal 1 to n cosine 2n plus 1 x cosine 2n plus 1 x over 2n plus 1 square converges uniformly. And to where? To absolute value of x. Why it converges uniform to absolute value of x? I mean, we know that it converges pointwise, and the convergence is uniform to the function. So this is good. Now, so the convergence of the Fourier series of my function, the convergence of the Fourier series is not only pointwise in this case, it's also uniform. Now, what about Fourier series of x? Now, you know that Fourier series of x is equal summation from n equal 1 to infinity of 2 times minus 1 power n plus 1 sine nx over n. Okay, and this I know that converges pointwise to where? Converge pointwise to f tilde of x, which is equal x when minus pi smaller than x smaller than pi, and at pi it's the midpoint, it is 0 when x equal pi, and to pi periodic. Doesn't converge to x, yes, it converges to where converge uniform to absolute value of x on minus pi, okay? because it's 2 pi periodic, so it converges uniformly to absolute value of x on minus pi and converges uniformly to the 2 pi periodic extension of absolute value of x to in R. This is the limit. On minus pi is x, and everywhere else it's not x. Okay. So let's see. Now, I know that this Fourier series converges pointwise to the following. So it converges pointwise to the following. Okay, then this I have here, and then I have this. Here I have this. This is the midpoint, and this is f of x. Now the convergence uniform. Let's try to use Weierstrass M test. You have 2 times minus 1 power n plus 1 sine nx over n. I know that this is smaller than 2 over n. Yes, but summation of 2 over n diverges. So inconclusive. So Weierstrass M test is inconclusive. By the way, the proof of Weierstrass M test proof math to 10. It's an easy proof, but I mean, it requires some. Now, a property or a theorem or a proposition, even proposition, if so given Fourier series of f at x equals summation from n equal 1 to minus infinity to plus infinity of absolute value of Cn e to the I n x and f bc1 of minus pi, if summation of absolute value of Cn is less than plus infinity, then Fourier series of f converges uniformly. Well, and the proof is quite straightforward. Proof: summation of Cn e to the I n x is equal absolute value of Cn. Summation absolute value of Cn converges. Then by Weierstrass and test, yes, so by Weierstrass and test I have what? I have Fourier series of f converges uniformly. In fact, you don't need here fbc1, okay? You don't need this. I mean, I didn't use PC1, converge uniformly to something, but we don't know what is this thing. Okay? It might be f, it might be something else. Okay. Now the application. Okay, so I will stop here this video, and then in the next video I will talk about the application of Fourier series. So now our next goal is to see. I mean, here I could not use Weierstrass M test in conclusion. I don't know if it converges uniformly or not. So, I mean, the whole goal now, for the next video, it will be to see that if I don't have this condition, if I cannot use Weierstrass M test, like here I could use Weierstrass M test. If I cannot use Weierstrass M test, can I know if how can I know that my Fourier series converges uniformly or not? Okay. For this, I need some properties of uniform convergence that unfortunately I cannot prove most of them, but I will give you what we need. Thanks.